What I'm going to talk about today is a different type of approach to deal with one of the problems that often students find difficult in this course, and that is a problem with relative velocity. And we're going to go back over an old problem. I have a problem and an example that I do with Newtonian mechanics and solve it a new way with Lagrangian mechanics. So what it is the same problem. You may remember this one. It's a 6 kilogram block B, which starts from rest and slides down on a 15 kilogram wedge A right there. Neglect friction and find the acceleration of the wedge and also what the acceleration of the wedge and the acceleration of the block relative to the wedge. The block is constrained to slide down the wedge, therefore the motions are dependent. Express the accelerations in the block as an acceleration of the wedge plus the acceleration of the block relative to the wedge. All right, so this is the standard Newtonian approach. Write the equations of motion for the wedge and the block. No problem, solve for the accelerations. So the block is constrained to move down the wedge. Therefore, the motions are dependent. So acceleration of B has to equal acceleration of A plus acceleration B relative to A. So if I start to write out terms, I have the kinematics right here, which is acceleration of A. So block B also has an acceleration of A plus an acceleration B relative to A. Great, no problem. And if I start to look at the forces between the two, I have a normal force from the block on the wedge, which is going to be N1 sine 30, and I've defined my X and Y here. I have weight acting downward. I have another normal. So in terms of X forces, I only have one, and that one force is the normal N1, which is equal to mass times acceleration of A. Great. So I have enough to work from there. I can put terms back in, substitute in, do a lot of work. Sum of forces in X is mass times mb acceleration of X, which is mb acceleration of A cos 30 minus acceleration of B with respect to A. Put all the terms in, and I get acceleration of B with respect to A is AA cos theta, or cos 30 plus G sine 30. Okay, great. And I get forces in Y, which are equal to just the weight term, and is equal to mass times acceleration of Y, which is equal to mass times A minus acceleration of A sine 30, because there's no Y acceleration of the block B relative to the wedge. So N minus MBG cos 30 equals M minus MBAA sine 30. Okay, no problem. Solve for the accelerations. I get all the terms there, 0.5 N1 mass times acceleration A, N1 minus MBG cos 30 equals minus MB sine 30. Put all the terms together, I get acceleration of A, which is MBG cos 30 twice MA over plus MB sine 30. Super. Acceleration of B with respect to A, I get acceleration of A, which is equal to, acceleration of B with respect to A, which is equal to acceleration of A, cos 30 plus G sine 30. So substitute in the terms that I would have found just before, 1.454 meters per second squared. Put all them together and get acceleration of B with respect to A of 6.24 meters per second, and previously, using the equation just above it, acceleration of A, which is 1.54 meters per second squared. So I've talked about this a couple of times. Again, this is outside of the normal lectures. Lagrangian equations take the same form in any coordinate system. Doesn't matter how you do it. And often they tend to be a little bit easier to solve when the problems get a little bit hairier. So forces of constraint are often eliminated with the Lagrangian, and a Lagrangian approach considers really a kinetic and potential energy. So it's often a scalar approach in terms of, and that could be advantageous. So you take the total derivative with respect to time of partial L partial xi dot and partial L partial xi. L is just the difference between the kinetic energy and the potential energy, T minus V. Great. It's great for working with conservative forces. Really powerful method worth knowing about. I have to sort of say, look, it's outside of the course material, But you may be interested just looking at it, especially when you're dealing with this problem and trying it out with this kind of problem and seeing what the differences are and whether or not you find it easier to get a result that you can sort of return to later. So same problem, Lagrangian mechanics approach. I'm just going to write everything out like this. So, xb is xa plus ab with respect to a, xa double dot. I'm just leaving everything now in terms of double dots, though. Okay, so these terms are accelerations, but it's accelerations as the second derivative of position. Total kinetic energy of A plus kinetic energy of B. Well, I can write that as 1/2 m xa dot squared. And then for the other one, I can write it as 1/2 mb xb dot sine squared theta plus x dot plus xb dot cos theta squared. Okay, so this is good. All right, not so bad. Potential energy, VA, VB. VA, the change in potential energy is equal to 0. That's my datum. VB is minus mb gb sine xb sine theta. So it's really just the change in height as I go along here. So if I write my Lagrangian, which is the difference between kinetic and potential energies, I get this right here. And since my potential energy is negative, it becomes a positive term. So x dot a squared, x dot a squared, x dot b, x dot a, x dot b, and xb. Now, this doesn't look like it's going to get easier. It's surprising, but it is actually, it looks like a very complex equation. So let's continue. So I have my expression here in terms of x dots and x, and I'm going to take, first of all, the Lagrangian for xa. So I take d dt dl, partial L partial xa dot, and partial L partial xa. If I take that first term on the left, I get ma plus mb xa dot plus mb xb dot cos theta. So I've got this derivative here. And I have this derivative here. This goes to 0, but this derivative stays and is multiplied across by 2. So that's where these terms come from. Same thing, take the derivative now, and those terms now go to xa double dot and xb double dot. This is really neat. I'm getting something kind of unexpected. If I take the partial of L with respect to xa, well, the only term that has an x in it, not x dot, is this one, and it's xb. So that term is going to go to 0. If I do the same thing for b, I'll get the same result, partial L partial xb, d dt. I'll end up with mb xa double dot cos theta plus xb double dot. Now, dropped one of the xa terms again because there's only a couple xb dot terms in there, so that sort of makes sense. But my partial L partial xb goes to mbg sine theta. This looks like a lot of work to keep up with it, but again, it's one of those problems that as you go through it, I kind of would like you to sort of try it on your own. Again, outside the lectures normally, but it's kind of a neat result. So you solve through, you've got these two equations, ma plus mb xxa double dot plus mb xb double dot cos theta equals 0. The other term you have is mb xa double dot cos theta plus xb double dot plus g sine theta equals 0. Substituting in terms, sort of manipulating a little bit, then I get two results, mb g sine theta cos theta, ma plus mb sine squared theta, and then on the other term I have ma plus mb g sine theta, ma plus mb sine squared theta. Okay, not looking good. Substitute in terms, hey, it looks exactly the same. I have acceleration of A and acceleration of B with respect to A. And so it's kind of a wild result. And it is a very different way of looking at these problems. It's less physics, more math, but honestly, it might be an easier way in some cases to look at these problems. And so I kind of encourage you to think about it as you move through all of this. Thank you, and we'll talk again.